Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This lesson, an introduction to vectors, is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. In this video, we will discuss the definition of a vector, properties of vectors, scalar multiples, vectors in a plane, vectors in space, the magnitude of a vector, and vectors in direction and magnitude. A vector, sometimes called a Euclidean vector, geometric vector, or simply vector, is a geometric object that has direction and magnitude. A vector can be expressed as a bold-faced italicized letter, usually U, V, and W, or a letter with a direction line overscore. Velocity, force, displacement, and acceleration are all examples of vectors. Quantities that have no direction are called scalars. Speed, mass, and distance are all examples of scalars. Vectors can be expressed mathematically as a direction line segment from an initial point P to a terminal point Q, denoted by PQ overscored with a direction line. A vector whose magnitude is 0 is called a zero vector. Two vectors, v and w, are equal, written as v equals w, if they have the same magnitude and the same direction. To add two vectors v and w, we position vector w such that its initial point coincides with the terminal point of vector v. The resulting vector from the initial point of v to the terminal point of w is the sum of the two vectors v plus w. We can also describe the addition of two vectors as the diagonal of the resulting parallelogram. Let u, v, and w represent any three vectors. The commutative property of vector addition says that v plus w equals w plus v. The associative property of vector addition states that u plus v plus w equals u plus v plus w. The additive identity property states that v plus 0 equals 0 plus v equals v. And the additive inverse property states that v plus negative v equals negative v plus v, which equals 0. If A is a scalar and V is a vector, then the product AV is called a scalar multiple of V. The following properties hold. If V and W are two vectors, and A and B represent scalar quantities, then 0 times V equals 0, 1 times V equals V, negative 1 times V equals negative V, A times BV equals AB times V. The quantity of A plus B times V equals AV plus BV. A times the quantity of V plus W equals AV plus AW. A vector whose initial point is at the origin is called a position vector and can be represented algebraically by the ordered pair V equals V1, V2, where V1 is the x component and V2 the y component. A vector whose initial point is not at the origin is equal to a unique position vector. We first designate the initial point as P1, having a position x1, y1, and the endpoint P2 having a position x2, y2. The position vector can then be determined by V equals P1 to P2 as a change in x and the change in y, or x2 minus x1, y2 minus y1. Every vector in a plane can be written in terms of the unit component of the vector 1, 0, designated with the lowercase bold letter I, added to the unit component of the vector 0, 1, designated by the lowercase bold letter j. This is called the standard basis vector, which equals v1i plus v2j. A vector in space whose initial point is at the origin is called a position vector and can be represented algebraically by the ordered triple v equals v1, v2, v3, where v1 is the x component, v2 is the y component, and v3 is the z component. A vector whose initial point is not the origin is equal to a unique position vector. We first designate the initial point as P1 having a position of x1, y1, z1, and the endpoint P2 having a position of x2, y2, z2. The position vector can then be determined by v equals P1 to P2 as a change in x, the change in y, and the change in z, or x2 minus x1, y2 minus y1, and z2 minus z1. Every vector in space can be written in terms of the sum of the unit component of the vector 1, 0, 0, designated with the lowercase bold letter I, the unit component of the vector 0, 1, 0, designated by the lowercase bold letter j, and the unit component of the vector 0, 0, 1, designated with the lowercase bold letter k. This is called the standard basis vector, which equals v1i plus v2j plus v3k. For example, find the position vector for the following, with P1 at the point 2, 3, and P2 at the point 6, negative 2, V equals x2 minus x1 and y2 minus y1. We replace the values to get 6 minus 2 and negative 2 minus 3, or the vector 4, negative 5, in terms of the standard basis vector 4i minus 5j. In another example, with a vector in space where P1 is 6, 2, 1, and P2 is at 3, 0, 2, the position vector is x2 minus x1, y2 minus y1, and z2 minus z1, or in this case, 3 minus 6, 0 minus 2, and 2 minus 1, giving us the vector negative 3, negative 2, 1, or in terms of the standard basis vector, negative 3i minus 2j plus k. The magnitude or length of a vector v, denoted by the symbol v with a double set of vertical bars, is the distance from the initial point to the terminal point of v. The magnitude of v is derived from the distance formula and is also called the norm of the vector v. By setting the initial point at the origin, then a vector in a plane, or the magnitude of v, is equal to the square root of v1 squared plus v2 squared. If v is a vector in space, the magnitude of a vector whose initial point is the origin is equal to the square root of v1 squared plus v2 squared plus v3 squared. For example, find the magnitude of the following vectors. V equals 4i minus 3j. The magnitude of v equals the square root of v1 squared plus v2 squared. Fill in the values to get the square root of 4 squared plus negative 3 squared. Simplify to get the square root of 16 plus 9, or the square root of 25. This makes the magnitude of our vector equal to 5. Secondly, v equals 4i plus 2j minus k. In the case of a vector in space, the magnitude of v equals the square root of v1 squared plus v2 squared plus v3 squared. Fill in our values to get the square root of 4 squared plus 2 squared plus negative 1 squared. Simplify to get the square root of 16 plus 4 plus 1, or the square root of 21. A vector with magnitude of 1 is called a unit vector. The following theorem applies. For any non-zero vector v, the vector u equals v over the magnitude of v is the unit vector that has the same direction as v. Multiplying a non-zero vector v by 1 over the magnitude of v to obtain a unit vector that has the same direction as v is called normalizing v. As an example, normalize the following vectors. V equals 5, 12. The magnitude of v equals the square root of 5 squared plus 12 squared, which simplifies to the square root of 25 plus 144, which simplifies to the square root of 169, or 13. The normalized vector u equals v over the magnitude of v, or 5 over 13, 12 over 13. The vector v equals 2i minus 5j plus 12k. The magnitude of v equals the square root of 2 squared plus negative 5 squared plus 12 squared. This simplifies to the square root of 4 plus 25 plus 144, or the square root of 173. Therefore, the normalized vector is 2 over the square root of 173i minus 5 over the square root of 173j plus 12 over the square root of 173k. Let's start by establishing a vector v as v1, v2. This vector can also be expressed as v1i plus v2j. Then we establish an angle theta as the angle between the vector and the positive x-axis. This makes sine theta equal to v2 over the magnitude of v, and cosine theta equals v1 over the magnitude of v. If we then normalize the vector such that the magnitude of v equals 1 with the same direction, then the normalized vector u can be expressed as cosine theta sine theta. This same vector can be expressed as equal to cosine theta I plus sine theta j. We can then express this vector using our other trigonometric rules, first by identifying the vector as a slope, which is the change in y over the change in x, which equals sine theta over cosine theta, or tangent theta, which equals v2 over v1. If we take the magnitude of cosine theta I plus sine theta j, we get the square root of cosine squared theta plus sine squared theta, which by trigonometric identity equals 1, the originally defined value of our normalized vector. From this, we can conclude that if v is a non-zero vector, and if theta is the angle between v and the positive x-axis, then x equals the magnitude of v times sine theta, y equals the magnitude of v times cosine theta, and v equals the magnitude of v times cosine theta I plus sine theta j. For example, find the vector v equals ai plus bj, where the magnitude of v is 4, and v makes an angle 30 degrees with the positive x-axis. From the theorem, we use v equals the magnitude of v times the quantity of cosine theta I plus sine theta j. Fill in the values to get 4 times the quantity of cosine 30 degrees I plus sine 30 degrees j. Cosine 30 degrees is the square root of 3 over 2, and sine 30 degrees is 1/2. Simplify to get 2 times the square root of 3i plus 2j. In our final example, a weight of 1,000 pounds is suspended from 2 cables as depicted in the graph. What is the tension on each cable? To solve this, we establish 3 vectors. F1 as the tension on the first cable, F2 as the tension on the second cable, and F3 as the weight of the suspended object. Since this system of cables is at equilibrium, then F1 plus F2 plus F3 equals 0, with the magnitude of F1 and F2 as the tension. We then establish I along the horizontal and J along the vertical to get F1 equal to the magnitude of F1 times the quantity of cosine 40 degrees I plus sine 40 degrees j. We measure the angle of F2 from the same origin as F1, therefore F2 equals the magnitude of F2 times the quantity of cosine 155 degrees I plus sine 155 degrees j. Since weight only has a vertical component, F3 is equal to negative 1,000 pounds j. Adding these 3 vectors together equals 0. Group the I terms to get cosine 40 degrees times the magnitude of F1 plus cosine 155 degrees times the magnitude of F2 equals 0. Secondly, the J terms group to get sine 40 degrees times the magnitude of F1 plus sine 155 degrees times the magnitude of F2 equals 1,000. Take the first equation and solve for the magnitude of F1, which equals negative cosine 155 degrees times the magnitude of F2 divided by cosine 40 degrees. Substitute this for the magnitude of F1 in the second equation. Sine 40 degrees over cosine 40 degrees equals tangent 40 degrees. Sine cosine 155 degrees times the magnitude of F2 plus sine 155 degrees times the magnitude of F2 equals 1,000. Factor the magnitude of F2 out of the equation to get it times the quantity of negative tangent 40 degrees times cosine 155 degrees plus sine 155 degrees equals 1,000. Next, divide the parentheses out so that the magnitude of F2 equals 1,000 over the parentheses part of the equation. This calculates to 845.24 pounds. Next, go back to the first equation, the magnitude of F1 equals cosine 155 degrees times 845.24 divided by cosine 40 degrees. This calculates to the magnitude of F1 equal to 1,000 pounds. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you, and good luck with your studies.